Thank you, Mary Beth, for the introduction. It's a pleasure to be here today, and I hope the attendees will find the next few minutes informative and that the information I share will help them have a safer experience when working with their hoods. Today we're going to focus on several areas that can make working with a fume hood more productive. My experience is that people assume that because there is a fume hood present in the lab, that the hood must be working properly and providing the intended level of safety and protection. If this fume hood were installed in a new lab you were about to occupy, would you question its performance? Wouldn't you just assume that because it's a new hood and a new lab that everything's okay? In reality, the fume hood is the most misunderstood and misused safety device in the lab. Many installed fume hoods are not providing the intended levels of safety. Today we'll go through some of the critical components and discuss their impact on the hood's overall ability to keep the user safe. Today we will look at the fume hood's purpose and function, the sash, turbulence and airflow, face velocity versus containment, making sure your fume hood is working, and the need for training. By addressing each of these areas, you will gain an awareness and understanding to make working with a fume hood safer, more productive, and maybe even fun. So let's jump right in and start by looking at what it is a fume hood does. First, we will discuss the fume hood's purpose and function. There are many things in the lab that look like fume hoods but are not. They're ductless ventilated enclosures, biological safety cabinets or BSCs, canopy hoods, educational hoods, spot extractors. But to be classified as a laboratory fume hood, there must be baffles, an operable sash, and it must be connected to a laboratory ventilation system. Laboratory or chemical hoods are not standalone devices like a biological safety cabinet or a ductless hood. In fact, the best fume hood in the world does nothing until it's connected to a properly designed, installed, and maintained laboratory ventilation system. The fume hood is just one component in a complex mechanical system. Yet when you look at the safety warnings posted on the hood, it often says, "Make sure the hood is working." So what does working mean? To answer that question, we need to answer another question. That question is, what is it that a fume hood does? The inside of the hood is called the fume chamber. This is where your work is done. Inside the fume chamber, there are 4 things the hood should do: capture, contain, dilute, and exhaust. The fumes, vapors, particles, and mist produced within the fume chamber should be captured. Once captured, they should be contained within the fume chamber and not allowed to escape. While they're in the fume chamber, they should be mixed with air and diluted to a safe level. Once properly diluted, they are then exhausted outside and away from the building. In the simplest of terms, when a fume hood is working properly, there is no loss of containment. Loss of containment exposes the user to various hazards. This is why the fume hood also belongs in another class of products called exposure control devices. Much confusion comes from the fact that the fume hood is a hybrid device. Not only is it part of a complex mechanical ventilation system, it is also a PPE designed to protect the user from various hazards. This hybrid classification is the source of a lot of misunderstanding. The fume hood is much like a 3-legged stool. To be stable and function properly, the stool needs 3 even legs. The same is true with the fume hood. Its legs are the fume hood itself, the laboratory ventilation system, and a properly trained user. So unless the fume hood's performance is viewed in this holistic way, the fume hood will not function properly. All 3 legs must be balanced and functioning correctly to protect the user. Now let's talk about the sash. From the user's point of view, it's all about the sash. The sash is the interface between the fume hood and the user. It's the primary feature that provides you with protection. The sash is a protective barrier between you and the bad and dangerous stuff. Managing the sash is largely common sense, and the lower the sash position, the better. While the sash provides protection, it is also a potential source of hazard. There can be contaminated air present at the edge of the sash. There can be a vortex of contamination just behind the sash. These vortices have the highest concentration of contaminants. You want to keep the edge of the sash or the sashes as far away from your breathing zone as possible. You may have heard the term breathing zone before, but generally it's the area from your chest to the top of your head. You want the sash glass between you and the bad stuff. And yes, there are different kinds of sashes. The most common is vertical rising, which is a single sash glass that goes up and down like a window. And then there are combination or combo sashes, which have sliding panels that move left to right and that are inside a vertically rising frame. Regardless of the sash type, the only reason you want the sash open, fully open, is for setup. A very common mistake is working with the fume hood in full open position. Lowering the sash is better. The sash movement should be easy. Many sashes can be operated with one hand from any position along the sash handle, and many newer hoods often have auto sashes that move with the assistance of a motor. Hood sashes are generally made from some type of safety glass, either tempered safety glass or laminated safety glass. This safety glass is used to offer you more protection and to minimize the likelihood of the sash itself breaking and becoming part of an incident. But whatever type of sash your hood has, keeping it closed when not in use and open as little as possible when using it is the right approach. The glass is there to protect you from the hazards. Fume hoods are very expensive to operate. They require large amounts of air to function properly. In most modern hoods, the amount of air the fume hood uses is determined by how much the sash is open. The smaller the opening, the less air and energy the fume hood will use. So generally, a closed sash uses much less air than an open sash. One of the fume hood's functions is to exhaust the polluted air outside and away from the building. As this air is exhausted, an equal amount of fresh air has to be supplied to the lab. This supply air has to be conditioned, heated or cooled, and the humidity has to be controlled. The real cost of operating the hood is replacing that air that's being exhausted. When you exhaust less, you need less replacement or supply air, thus saving money. While you might not have thought much about it, fume hood fires are another common hazard. While there are many reasons for fires, let's look at the role of the sash when a fire happens. In case of a fire, close the sash completely to minimize the amount of air feeding the fire. The sash also keeps the fire inside the hood and minimizes its spread. The proper action when a fire does occur varies. You need to understand the SOP of your lab and respond accordingly. This is a very complex topic that varies from lab to lab, and because of its complexity, we offer a training module that focuses just on fume hood fires. Fires are very dangerous and expensive events, so preventing them should be an overriding objective. Small fires can quickly spread and become a major event. In fact, a small fire resulted in the death of a researcher at UCLA, partially because she was not wearing a lab coat. Given the material she was working with, she should have not only been wearing a lab coat, but a fire retardant lab coat. Not only do fires harm people, they damage equipment, destroy work, and even a small fire can take a building out of service for months, displacing the users and destroying research. But fires do happen, and the sash is there to protect you. Back to your breathing zone. Given the complexity of laboratory ventilation and room conditions, it's nearly impossible for any hood to contain 100% of the time. We can almost guarantee some loss of containment. In many of the demonstration videos, we use smoke or theatrical fog to help you visualize the airflow and show loss of containment. But in real life, the fugitive chemicals are likely to be invisible and maybe even odorless. So what you can't see can harm you. Whether or not you inhale those fugitive chemicals is greatly influenced by the position of the sash in relationship to your breathing zone. Keeping the sash closed as much as reasonable helps protect you. Now let's talk about explosions. They come in all shapes and sizes and can be caused in many different ways, from a boiling breaker exploding to an explosion caused by flammable vapors. The most common byproduct of an explosion is shrapnel. In a fume hood, the most common shrapnel is broken glass. And with broken glass often comes chemical splashes. Again, the sash is there to be a barrier between the event and you. Like fires, explosions are all too common. They're harder to predict and harder to prevent. The difference is that the damage is usually concentrated on those using the hood or those nearby the explosion. Remember, from the user's point of view, the fume hood is a PPE. It's also important to understand all the PPEs and safety devices that a fume hood user should be aware of. The standards are lab-coated safety glasses. They're a must. Things like gloves, face shields, goggles, maybe even a respirator may be appropriate depending on what you're doing. You need to understand the risk and hazards of the material you're working with. But just in case there is an incident, you should also be aware of things like the fire extinguisher, the eye wash, and the safety shower, and know how to properly use them. The sash is there to protect you, and the degree of protection depends on how you use the sash. Now let's talk about turbulence and airflow. While these are higher level concepts, it's important to understand the basics so you can maximize the hood's performance. This is probably a good place for an analogy. Let's compare the fume hood to a car. The car and the fume hood are both complex mechanical systems. As an operator, you are responsible for how the car is used. But as a driver, we would not expect you to fix the mechanical issues. But we would expect you to know when the auto wasn't performing correctly and be able to convey the symptoms to the mechanic. The same is true with the fume hood. You should understand enough about how it should be performing to report issues to those responsible for its mechanical performance. First, let's acknowledge that generally we can't see air. If we could, much of what we'd be talking about would be merely common sense. It's important to know that air and water behave the same. Both follow the same physical laws of fluid dynamics. Air is a fluid. Think about a major water leak in your house. Inches of water everywhere, in every room. You need to squeegee it all out. Think how difficult it is to move that water around and get it to go where you want it to. The same is true with air. An engineer once told me managing airflow was like herding frogs. Mechanical ventilation and fume hood performance are anything but simple, but having a general understanding of what the air is doing allows you to do things that will make the hood work better, and to spot things that may be impacting its performance that need attention by the facilities or maintenance people. Just like water running downhill, air flows from high pressure areas to low pressure areas. In a fume hood, the low pressure area is the plenum. The plenum is the space between the baffles and the back wall. There is an opening at the top of the plenum where the ductwork is attached. Then there's a fan, usually on the roof, that creates the lowest pressure for the entire system. You could say that the fan is sucking the air through the hood. Airflow is designed to flow from clean to dirty areas. The clean air from the corridor flows into the lab. The lab air flows into the hood through the sash opening, then into the plenum, then the ductwork to the exhaust fan where it's usually exhausted out of the building. Any imbalance can cause the direction of the flow to change. Managing the room pressurization is a real challenge to fume hood performance. Pressure changes can reverse flow, which can result in unsafe conditions in the lab. In a properly designed and balanced lab, the lab is under slight negative pressure compared to the hallway. If you crack the door, you usually can feel the air rushing in. The fume chamber has to be lower in pressure than the room to draw the air into the plenum. While this all looks simple on paper, it's anything but simple in reality. Maintaining proper balance is critical to the hood's safe performance. Airflow is typically not something the user can control, but it is necessary to have a general understanding to verify that the hood is working properly. But there are some components of airflow that the user can control. Let's say that everything is balanced and working properly. There's air entering the fume chamber through the sash and over and under the lower airfoil. Given the pressure difference, the air is trying to flow across the work surface to the lower slot in the baffle. But if there's objects directly on the work surface or in front of the baffles, you disrupt that airflow. Think of air as if it were water flowing down a river, smooth and calm. Now put some boulders in the river and the smooth flowing water turns into rapids. Objects in the hood do exactly the same thing to the airflow. These objects can create enough turbulence to cause the hood to lose containment, which could contaminate the lab air and create hazards for the users, the equipment, and the work. As a user, there are things you can do to improve performance. Don't block the baffle openings. Keep objects away from the sidewalls. Elevate objects so they don't sit directly on the worktop. This allows the air to flow under them on its way to the baffles. Work 6 inches behind the sash to prevent chemicals from being drawn out. Move slowly and deliberately within the hood and when you remove objects. All of these things must be adhered to for the fume hood to have a chance of keeping you and your colleagues safe. Now let's look at turbulence. Fume hoods are very turbulent devices. If you could see airflow and it were reddish orange, it'd look very much like the flames of a fire. Pressure changes are continuous, and that impacts the airflow. Much like a campfire, no 2 seconds are exactly the same. It is as if the fume hood were breathing. You've probably seen fume hood tests published by manufacturers. These tests are valid and useful, but you should understand how the tests were performed. Fume hoods are rigorously tested at the factory to ensure their performance. Fume hood manufacturers do the ASHRAE 110 AM or as manufactured test with an empty hood in a test room under perfect room conditions. The reason for this test is to separate the hood's performance from the influences of the room. This allows you to do an apples-to-apples comparison of various hoods, but it doesn't tell you how that hood will perform in your lab. In the lab, we never work with an empty hood, and we never have room conditions that are perfect. Room conditions are changing minute to minute, even in the best labs, and the room conditions are far from perfect. In fact, in a lab building, the airflow in individual rooms resemble ocean currents with tides and ebbs, continually moving and changing. Your body also causes turbulence. When you stand in front of a hood, your body acts much like an airplane wing. There is a low pressure area created in front of you. This low pressure area can suck out chemicals from the hood. That's why we work 6 inches into the hood, so the chemicals are less likely to be drawn out. The critical 6 inches allows the hood to contain at a much better rate. Now, walk past the hood with an open sash. That low pressure area is now behind you. As you walk by, it can suck chemicals out of the hood. Also, if you move your hands in a fast manner inside the hood or quickly remove objects from the hood, you can draw chemicals out. All these events are loss of containment. The fugitive chemicals can be inhaled by those at the hood, and they also pollute the air in the lab. Another source of turbulence is cross drafts. The most common cross drafts are caused by high velocity supply air registers being too close to the face of the hood. Also, when we have hoods too close to the door or too close to each other, there can be cross drafts. The magnitude and direction of the cross draft determine the potential impact on the fume hood's ability to contain. Turbulence is a primary factor in the loss of containment. Reducing turbulence can help the fume hood better contain. A component of turbulence is velocity. The faster we move in and around the hood, the more turbulence we create. The faster we open and close the sash, the more turbulence we create. When working with a fume hood, slow and deliberate movements are best. At the end of the day, there's only one way to know that your fume hood is performing, and that's to have it tested as you're using it. Face velocity versus containment. There's a major misconception that if the face velocity shown on the hood alarm reads 100 feet per minute, then the hood must be working. But there is no direct correlation between face velocity and containment. Let me repeat that statement. There is no direct correlation between face velocity and containment. Just because the fume hood has 100 feet per minute face velocity does not mean it's working safely. In fact, when doing ASHRAE 110 testing, over half the hoods that failed containment testing had the specified face velocity. While face velocity is a component of containment, it's only one component. How fast the air is going into the hood, which is the face velocity, merely determines how big the rapids and turbulence will be. Raw face velocity is more about turbulence. The direction of the airflow is determined by differential pressure. The stronger the negative pressure at the back of the fume chamber, the more aggressively the air moves into the low pressure parts of the hood, which is mainly the plenum. Again, the plenum is a space created between the baffles and the back wall of the hood. This special hood was constructed with clear baffles so you can see inside the plenum. By using colored smoke, you can see the path the smoke takes to the exhaust duct. Face velocity is a useful number and provides some indication of overall performance. You should only work at a fume hood that has a velocity alarm and the velocity is within the specified range. Here in the U.S., you will find that hoods were designed to operate between 60 feet per minute and 100 feet per minute. Occasionally we'll find hoods with higher or lower design velocities. While 100 feet per minute has a logical basis, as the face velocity goes higher, particularly over 125 feet per minute, excess turbulence is created, reducing the hood's ability to contain. So more isn't necessarily better. And too low you're more likely to have external movements cause loss of containment. Again, the way you know a fume hood is performing at a specified velocity can only be determined with an ASHRAE 110 as-used test. It often helps to visualize airflow within the hood. Not everyone has access to a fog machine, so another way to visualize airflow is to pour warm water on dry ice. It is often said that if you can't see a problem, you can't fix it. Fume Hood Certified is starting to post videos on our YouTube channel that will help you visualize some of the issues we are discussing. Today, most labs have VAV or variable air volume controls. Remember, for your hood to function safely, the room has to stay balanced. That means that the room remains slightly negative to the hallway, and the amount of supply air at any given time is roughly equal to the amount of air the fume hood is exhausting. So we have both exhaust and supply volumes to manage. Let's say the hood has an experiment running and you have the sash closed. The amount of air the hood is exhausting is low. The room's supply air terminal has closed down to keep the supply air coming in equal to the amount of air the hood's exhausting. Now you open the sash and the exhaust volume suddenly increases. But there's a lag time between when the room controller recognizes this volume or pressure shift and readjusts the supply to get back to a stable condition. During this period of lag and instability, a fume hood is more likely to have a loss of containment due to the differential pressure changes. Yet it is highly possible that the face velocity has remained within an acceptable range. Remember what I said, there's no direct correlation between face velocity and containment. Before there were digital alarms, hoods were often equipped with manometers. These gauges read differential pressure. But because these readings were always fluctuating with the pressure changes, which was actually a better indication of containment, it was difficult for the user to determine when the hood was performing safely and when it wasn't. The thinking was that a velocity monitor would be a better solution since it could be programmed to alarm when the face velocity was outside the specified range. Yet over the years, I've seen hundreds of people working with hoods that were alarming, and rather than addressing the problem, they would simply mute the alarm. While the face velocity alarm is not perfect, it is better than nothing and should be used as an indication of basic performance between regular hood tests and calibrations. Making sure your hood is working. We've come somewhat full circle. How do you make sure your fume hood is working? The simple truth is there is really no way to know for sure. But there are things we can do and should do to improve the likelihood of it performing safely. The first thing you can do is understand what is your hood working means and be aware of the signs that it isn't. When you identify those red flags, that they should be reported so they can be addressed. Next, you should know who is responsible for your hood's performance. If someone isn't responsible, no one is responsible. Each organization can have a different organizational structure. Responsibility for safe performance can range from the user to maintenance to EHS to a safety officer or compliance officer. Again, this hybrid nature of the fume hood, being both an engineering control and a PPE, tends to cloud responsibility. Do your part in ensuring that you have properly trained on the use of the fume hood and make sure you're using best practices when you're working at the hood. Like most safety equipment, there should be a regular checkup for the fume hood, at least annually, and ideally twice a year. A trained inspector can spot many problems that can be addressed, often easy fixes. Then there are self-audits that the user and the lab manager can do. Internal EHS and facilities people can perform various types of testing, and when problems are suspected, an outside tester or troubleshooter can be brought in. You shouldn't work at a hood that doesn't have a current certification sticker on it. And remember that the hood is also part of a large mechanical system that requires regular calibration and maintenance. How often do they check the fire sprinkler system in your building? A laboratory ventilation system is much more complex and just as important. Shouldn't the ventilation system be inspected as frequently? With a fire sprinkler system, you generally only see the sprinkler heads in the lab. You don't see all those pipes, controls, and pumps that make it work. The same is true with the laboratory ventilation system. All you see is the fume hood itself. You don't see all the things above the ceiling and on the roof that are necessary for the hood to work correctly. So having a safe and energy efficient hood is a holistic endeavor that requires many people working together. But at the end of the day, it's the user's health and safety that is at risk. As a frontline person, make sure you're doing your part. By understanding the fume hood's function and knowing the signs that your hood may not be working, you're in a much better position to get the problems corrected. You are a critical part of the overall system. The need for training. PPEs, as simple as an N95 mask, require fitting and training. So why not a fume hood? The answer comes back to that hybrid nature of the hood. It is more often classified as an engineering control rather than a PPE. As such, a hood's performance is often considered outside the control of the user. Yet, after testing thousands of hoods, we know that at least 25% of fume hood performance failures are caused by user work practices. As a user, you're an important part of the system. When giving workshops and speaking at conferences, I often say you may not have the budget to replace poorly performing hoods. You may not have the budget to fix poorly performing laboratory ventilation systems. But the one thing everybody can do is train their users. Training alone can fix a quarter of the problems and probably reduce the number of injuries and deaths caused by preventable accidents. Labs are inherently dangerous with numerous hazards, but training can make them safer places to work. Fume Hood Certified is an education and training company. Our mission is to make labs safer one fume hood at a time. We are continually developing new courses that focus on real-world needs of users. If you have a special situation or would like to be a program tester for our courses, please contact us. Due to the complexity of laboratory ventilation systems, there are many things that impact performance that are outside the user's control. We want you to be aware of what you can control and at least understand what a properly functioning hood looks like. So when you feel your hood may not be functioning properly, you can report it to the proper people and have it checked. You might also compare this to a medical event. You have a fever, you feel horrible, but you have no clue what the root cause of the symptoms are. But these symptoms tell you something is wrong and you should seek medical attention. Just because the fume hood's in your lab, don't automatically assume it's working properly. Situational awareness is key to your safety and well-being. This covers the topics we've outlined in the beginning, and now I'd like to thank everyone for spending this time with me. I'd like to thank Lab Manager for putting this webinar together, and all of you for giving me the opportunity to share some of my fume hood experiences with you. But we're not quite finished. I'd be happy to answer a few questions. Mary Beth, do we have any questions?